Welcome to the session on vectors, solving geometric problems. The objectives for this session are to use vectors to solve geometric problems and find the position vector of a point dividing a line segment in a given ratio. Suppose the point P divides the line segment AB in the ratio lambda to mu, as shown in the diagram. So AP to PB equals lambda to mu, as shown. Suppose this is the origin here, and it joins A, and it also joins B and P. Then OP equals OA plus a fraction of AB. This fraction is lambda over lambda plus mu. And then replacing AB with position vectors gives us the expression shown here. So let's apply this to an example. Points A and B have position vectors little a and little b, respectively, referred to the origin. The point B divides AB in the ratio 1 to 3. We are required to find OP. So let's have a look at this. Here's AB. It's divided into AP and PB, and you can see the origin as well. The origin joins A, B, and P, as shown. If we apply our formula to this example, we obtain OP is equal to OA plus 1, which has taken the place of lambda, over 1 plus 3, which has taken the place of mu, times AB. And if we tidy up, putting the OA's together, we obtain 3/4 OA and the OB, which is 1/4 OB. And this, of course, is 3/4 A plus 1/4 B, where little a and little b are the position vectors. Now let's take a look at some theory relating to non-parallel vectors. So if A and B are two non-parallel vectors and pa plus qb equals ra plus sb, then we have that P equals R and Q equals S. Let's take a look at an example. The parallelogram OABC has a point P where the diagonals OB and AC intersect. The vectors A and C are equal to OA and OC respectively. Prove the diagonals bisect each other. So let's take a look at the diagram and solve this problem. From the diagram, we have that OB equals OC plus CB. This equals C plus A. And CB is equal to A, because CB is parallel and equal to OA. We also have that AC equals AO plus OC. And of course, AO is equal to minus OA. And OC remains the same. So we have that AC is equal to minus A plus C. And so we have AC equals minus A plus C. Now P lies on OB, as you can see from the diagram. And since OB equals C plus A, OP must be a scalar multiple of C plus A. Also, we have that P lies on AC. So therefore, OP, which equals OA plus AP, is equal to A plus a scalar multiple of minus A plus C. Since we have that AP is a fraction of the line AC. In particular, P lies on the line AC. And of course, this implies that lambda times C plus A is equal to A plus mu times minus A plus C, because both of these expressions are equal to OP. And so rearranging gives lambda A plus lambda C equals 1 minus mu times A plus mu times C. And since A and C are not parallel, we can conclude that lambda equals 1 minus mu and lambda equals mu. And so we have from both these equations that lambda equals 1 minus lambda. Rearranging this gives us that lambda equals a half. And since lambda equals mu, we have that mu equals a half also. And therefore, P is the midpoint of both diagonals. Since P lies on OB and AC, and OP equals a half times C plus A. And therefore the diagonals bisect each other. And we have proved our example. Now let's have a go at another example. In triangle ABC, AB equals 7i minus 2j and AC equals 5i minus 7j. Find the size of angle CAB in degrees. Let's see how we can tackle this problem. We can either find the lengths of the three sides and then use the cosine rule, or convert the vectors to magnitude direction vectors and then find the third angle. So let's solve this. We're going to use method 1. The length of AB by Pythagoras equals the square root of 7 squared, which is AB in the x direction, plus minus 2 squared, which is of course AB in the y direction, to give us square root of 53. Similarly, the length of AC is equal to the square root of 5 squared plus minus 7 squared, which equals the square root of 74. Now the vector BC equals BA, and of course BA is minus AB, plus AC. And then adding the two vectors gives us that BC is equal to minus 2 minus 5. And therefore, again using Pythagoras, we have that the length of BC is equal to the square root of minus 2 squared plus minus 5 squared, which equals the square root of 29. Now recall the cosine formula. We're going to plug in the values of little a, little b, and little c into this formula to find cos A. So here's little b, which equals root 74. It's opposite the angle B, or capital B. Here's little c. It's opposite the angle capital C. The length is mod AB, and it's equal to root 53. And here's little a. It's the length of mod BC, and it's opposite the angle capital A, and it equals root 29. And of course, the 2 is part of the formula as well. And so, tidying up and calculating, gives us that cos A equals 0.782. And therefore, if we inverse cos, we obtain A equals 38.6 degrees. This brings us to the end of this session. If you have understood its contents, you should be able to use vectors to solve geometric problems and find the position vector of a point dividing a line segment in a given ratio. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.